All right, at liftoff, a rocket weighs 40.6 tons, including the weight of the fuel, and it's fired vertically. The fuel is consumed at a rate of 2.16 tons per 1,000 feet of ascent. How much work is done in lifting the rocket to an altitude of 10,000 feet? So what we've got is this rocket, and it kind of helps sometimes to draw a picture of what you're dealing with. So we've got this rocket, looks like this. It's got flames coming out of the bottom because it's launching, and so it looks, there we go, rocket launch. All right, and rocket and fuel together weigh 40.6 tons, and we want to find out how much work is done by the time the rocket moves out to 10,000 feet. Okay, and we're going to also just say, hey, for simplicity's sakes, the rocket is just moving straight up and down. Most times, especially from Kennedy Space Center, that rocket is launched at a little bit of a tilt, not a very much of one, but it kind of arcs out over the ocean. So we're not going to talk about what would happen in that situation. It tells us that fuel is consumed at a rate of 2.6 tons per 1,000 feet of ascent. That means that we're losing tonnage as the rocket is launched. And so while that's happening, we would say that we start off with this weight, and it's a constant rate of change down. So what we want to do is we want to integrate from 0 to 10,000 feet the linear equation that we would get to show the rate of change for the loss of the tonnage. In other words, fuel and all that kind of stuff. So I start at 40.6 tons. That's my y-intercept. And then I'm losing weight, so I'm going to subtract the rate at which I'm changing, which is going to be 2.16 over 1,000 feet. And so this guy right here is the equation that we want to integrate. So we're just going to put that in here. 40.6 minus 2.16 over 1,000. And we're going to go ahead and use x as our variable. And then you can punch this into your calculator. It also integrates out by hand, not too badly. When I do this, I end up with 298,000 foot-pounds of force, or of work, that's done to lift that rocket from 0 to 10,000 feet. All right, now same situation, but we got a leaky bucket. And the leaky bucket holds 280 newtons of water. It's lifted from the ground at a constant rate to a point 50 meters above the ground. The bucket leaks at a constant rate and just finishes draining as it reaches the top. So how much work is done lifting the water to a point 50 meters above the ground? Do not include the rope and bucket. Well, same situation as we were looking at with the rocket. We start off with this bucket of water, and we're just talking about the water only. And the water is 280 newtons worth of water. Okay? And we're going to lift that bucket of water up 50 meters. So what happens is, as we lift the bucket, the water is constantly draining. And by the time we get to 50 meters, it's finished. So how much have we done? How much work have we done? Well, we started off with 280 newtons. And we're losing the newtons at a constant rate. So let's go ahead and say 280 divided by 50. And x, because depending on where we're at in meters, depends on how many newtons we have left in our bucket. We can't have more than 280, but we could have up to 280. And we're losing it as it goes. So then we can set up our integral from this. And our integral then sets up from 0 to 50, because that's how far we're moving the bucket. We're moving the bucket 50 meters. And we're going to integrate the equation that we got, which is going to be 280 minus 280 over 50 times x. And you can reduce 280 over 50 if you're one of those kind of kiddos that doesn't like to see extra zeros or whatever. And again, integrate this guy. He doesn't integrate too badly by hand. My kids can use a calculator. But when you punch this into your calculator, you get 7,000 joules of work that need to be done just to lift just the water. Now, if you're also asked about the bucket and the rope, the bucket is constant. The weight of the bucket wouldn't change, but the rope also changes exactly like the water changes. And then you would find the work for all of those and all of them up. All right, so there you go, lifting a leaky bucket. Okay, we've got the end of a pool. Is a vertical wall 18 feet wide. What is the force exerted on this wall by the water if it's 5 feet deep? So let's just get a real quick, whoops, we don't need that. Let's get a real quick 3D picture of what this might look like, and then we'll break it down. So we've got some pool. We're not given a ton of information about the pool, but it's going to look something like this. And it's got 5 feet of water in it. So here's our water line. Purple water. Let's go with blue. Blue water. So here's our water line. And what we're wanting to do is investigate how much pressure is being put on the end of the pool. So what we're going to do is we're going to look at this part of the pool right here, from here to here, and from here to here, okay? So I'm just going to only look at that end. So we're 18 feet wide. We've got water that's 5 feet deep. So here's our water in here. And the water is 5 feet deep. Okay. What I want to do is I want to integrate a little teeny tiny slice of area from this end, okay? So how do I figure out where that is? Well, I've only got 5 feet of water, so I'm gonna, and if we think about this as moving along X and Y, okay? So here's Y, here's X. So if we think about it in that way, then I'm gonna have 5 minus Y as my depth, okay? Depending on what value of Y I've got, depends on where I'm taking my slice, okay? My slice is 18 feet wide, and I'm looking at an infinite number of slices, okay? So this gets me my area, this gets me my volume, and then the last thing I need is this density of water, which is this cat right here, and he's 62.4. So whatever number I get in this is going to multiply with 62.4, okay? The other thing that's important for this is the limits of integration. And because we're dealing with 5 feet of water, I'm only interested in what happens between 0 and 5. I don't care what happens outside of that, just from 0 to 5. So again, this is a problem that you can integrate fairly easily by hand. The 62.4 can be a little difficult to multiply out. I did it on my calculator, and I got 14,080 pounds of pressure. Okay? And so that's really all there is to it. It's not like a super tricky, super hard question. So it is asking us to think about force a little bit differently. All right? So basically, what are we doing? We're integrating the area of the cross section, okay, times dy, and that will give us the pressure of the fluid.